Well, thanks for inviting me. It's been a stimulating visit so far, and I look forward to the rest of the week. I'm going to tell you about some new work and some now a little bit older work that I've done with the Kepler spacecraft data. This actually goes back more than a decade to my time as a Chandra Fellow. And whereupon hearing a talk about transiting planets, I got thinking about what's the difference between a transit and a microlensing event, which are both depicted here. Transit of the or eclipse of the sun by the moon, and a really high magnification microlensing event that I imagine some folks at Princeton were involved in. So I worked on the equations unifying these two phenomena, and the technical term for both of these is one body going in front of another. And whether you get a transit or an eclipse or microlensing depends on the ratio of the Einstein radius, which I've written out here for a body that's close to a source body. So this would be relevant, say, for the same major axis A of a planet or a star in a binary. The mass of the foreground object, which I've called M2 here, times 4g over c squared. Take the geometric mean of twice the short shield radius and the same major axis, and that gives you the Einstein radius in that limit, in which both the lens and the source are very distant. So when the Einstein radius is greater than the size of the foreground object, then you get gravitational microlensing, and that occurs when the object is very small or very massive, or the same major axis is very large. So you get a really large Einstein radius relative to the size of the object. In the eclipse case, or the transit case, the Einstein radius is much smaller than the size of the foreground object, and so it blocks the light, and the rays, even though they're magnified slightly, don't give much magnification. You do get some, but it's usually undetectable for a planetary transit. And so in that case, you get a transit or an eclipse. So I'll talk about both of these phenomena today, but I'm going to start with the transit phenomenon, which is really why the Kepler spacecraft was built. And it's done a survey, an initial survey, K1 or K0, of 150,000 stars or so, taking an exposure every half hour for over 4 years. And this has really been a boon for exoplanet science. If every planet system was like our solar system, this would have been a very boring mission. Instead, they found many, many short period planets orbiting other stars, and these planetary systems were fairly coplanar. And so they found something like 465, this number's out of date now, multi-planet transiting systems, so multiple planets transiting the same star, and periods less than a day out to hundreds of days. They've found multi-planet systems with 5 or more planets. We actually found one with 7 planets transiting the same star. Rocky planets have been found. And by rocky, I mean that with a radius and a mass measurement, they're consistent with having similar compositions to the Earth. I'll touch on that a bit. Planets orbiting around binary stars have been found. In one case that we're working on, there's actually 3 planets that transit one of the stars in a binary star system. And it's a lot of data to go through. It's difficult sometimes to separate the wheat from the chaff. Some transiting planet candidates may not turn out to be legitimate planets. There's crosstalk across the detector. There may be blends with eclipsing binaries that can mimic a transiting planet. And so there's 4,600, well, that's number's out of date. I think it's up to about 7,000 planet candidates now that are being studied with follow-up observations to confirm that they're actual planets and not some other phenomenon. It's difficult to validate these with radial velocity measurements because by its nature, Kepler could only look at 1/400th of the sky. Still a lot of the sky, 100 square degrees roughly. And so it's limited to the brightest stars in that field, which are dimmer than the stars that you can pick off with radial velocity searches, which are star by star, and so they can cover the entire sky and use brighter stars. But many planets have been confirmed with radial velocity measurements around the brightest stars that are transited in the Kepler survey. So the way Kepler finds transiting planets is by folding the data on various orbital periods and looking for a transit reoccurring periodically. But this can be problematic when you take into account the gravity of the planets. Planets interact, and over time, that can change their orbital period slightly. In some cases, it can change it enough that the transit times vary by more than the transit duration, and so when you fold the data, that smears out the signal. And so this shows a simulation of a transiting planet. You can maybe make it out by eye with it's close to a 2-to-1 period ratio in resonance, a 10-to-1 mass ratio. This is the smaller mass planet, super Earth and gas giant sort of masses. And it's really difficult to see this planet, and if I cranked up the noise or decreased the signal a bit more, the Kepler pipeline would miss this. If instead I take all the transits, this is folded on the mean orbital period, if I take all the transits and realign them by the variations in the time to transit, the signal pops out easily. So that's the same data, but now all the transit times have been realigned. And so this was something we were concerned about a few years ago. I talked with Josh Carter about this. I relied on the most powerful research tool to solve this problem, which is a Google search. So I did a search for quasi-periodic pulse detection, and out popped this abstract as the first search term. It probably still is if you type it into Google right now. A posteriori joint detection and discrimination of pulses in a quasi-periodic pulse train, which is exactly what we wanted to solve this problem. It was pretty amazing, actually. They looked at this problem for various other applications, including electronic warfare, radar, communications, geophysics. They didn't mention transiting planets. But what the problem that they solved was optimization of fitting a series of pulses to a uniformly sampled data set, which is perfect for Kepler because half-hour exposures. And the constraint was that the indices between pulses, which are just labeled by integers since it's uniformly sampled data, have to lie within some range that you specify. And the algorithm efficiently solves this. And so Josh Carter and I implemented this and started searching through, initially, the Kepler data, which had known transiting planets in the hopes that there might be additional planets. The first one that popped out was pretty remarkable. This shows what a periodogram search comes out of this. So you have to specify a minimum period and a maximum period. And so there's some window of slop at which the times between transits can vary due to dynamical interactions. And so we specified that, and then the mean between those two gives you the orbital period. And so when you do a search through a Kepler light curve as a function of orbital period and calculate the signal to noise of various candidate signals, then at any trial orbital period, you'll pick up on a planet that lies within that range from Tmin to Tmax if it's periodic. And if there's some transit timing variations, then you have to widen the window to capture that variation. Actually, when I was working on this, my brother helped me out a bit in trying to explain this shape of the spectrum. And what you see here is a series of commensurabilities between the correct orbital period. If you choose twice the orbital period, then you can find the peak height by the fact that you're, let's see, missing every other transit, and so your signal noise goes down by the square root of 2. In general, your signal noise scales as 1 over square root of m times n. To find m and n, this is what Ian helped me with, was you have to find the integer ratio in that period range that you're searching that is closest to the integer to the ratio with the actual orbital period. You can do that with Ferry addition, and using the Ferry sequence, you can find the largest m and n values that fall within that range of periods that you're searching. When you do that and then use this formula, you get this blue dash curve, and it matches the spectrum exactly analytically. So that then you can use that as kind of a template for finding whether you found a real planet or not. OK, so this was the first thing that popped out. Well, it wasn't the first one, but the best one of this first search for quasi-periodic transiting planets. This is known as Kepler 36b and c. C has very deep transits. This is what we've called a river plot, where each row is a transit of the planet, and green represents brighter, blue represents dimmer. And because you can see the clear blue and green here, each of these transits is easily detectable by eye. There are some, 55 odd transits here. So this one was actually found by the Kepler pipeline because the transits were clear enough that it picked it out easily. This one you can see looks less like a river, more like a marsh, and that's because this transit depth is smaller and it's comparable to the noise, so each transit is maybe a couple sigma. But with 65 transits, you can actually build up something like 20 sigma detection. And what you see here is that the data for each transit, each row, is aligned to the mean orbital ephemeris. Gray is missing data. Some of the transits occur later and some occur earlier. And you can see that there's anti-correlation because of conservation of energy and angular momentum between the two planets. You can also see that when the planets pass one another in their orbits, they're closest to one another. Gravity goes as 1 over r squared, so they give each other a kick. And you can see a jump in the times of transit of our best fit model, which is indicated in red, that occurs after the two planets have a closest approach, a conjunction. From that, you can actually get very precise masses and constrain the eccentricities of these planets. We actually did a photodynamical model which matches the data perfectly. The residuals look like pure noise. And the photodynamic model means that we integrate the orbits and then compute the transit profile of the planets going in front of the star and just fit that directly to this data set that's being plotted here. The results of that give the most precise mass of a super Earth size, so 1.45 Earth radius planet, about 4.5 Earth masses, that's consistent with taking an Earth composition and scaling it up. So 70% rock, 30% iron, roughly. That equation of state of radius versus mass goes right through the posterior distribution. This is 1 and 2 sigma of Kepler 36b, and the gray scale is just showing the cloud of posterior distribution points from the Markov chain Monte Carlo. Both Josh and I ran independent analyses, and we got the same answer. Its companion, the planet that was easily detected initially, is about 8 Earth masses and 3.7 Earth radii. That is consistent with a 7.5% hydrogen-helium envelope. This particular model was computed by Eric Lopez, and of course Adam Burrows and collaborators have done very similar calculations. And so this is by volume mostly hydrogen-helium, but by mass mostly probably, we guess, a core, possibly very similar to Kepler 36b, the rocky small companion that was first missed by the Kepler pipeline. Okay, so this got us excited to see if we could find other planets missed by the Kepler pipeline. And so I'll show you now a couple of other examples. This is a candidate found by my graduate student Ethan Cruzy. This planet at 7.55 days was initially found by the Kepler pipeline. In the initial search, the ephemeris was roughly constant, but then it did a right turn. For some reason, this other planet, not too small, much smaller depth, but maybe a bit noisier per transit, was missed by the Kepler pipeline, and our CAT search found this second planet. What's interesting is both of these have a size that's about the size of Mars. Unfortunately, they haven't completed a cycle of variation within the time of the Kepler data set. So over 4 years, they're still in this parabolic trend. That actually causes some problems with the analysis of the dynamics of this system, but this is still a work in progress by my student. Another candidate that was missed initially by the Kepler pipeline is in a system called KOI 1353. This shows a planet with a 35-day orbital period, many transits detected within the Kepler data set, 40 some odd. So again, each of these is one transit. And then a giant planet companion out of 125 days, every single transit is very clearly detected. and there's a dozen or so transits within the Kepler data set of this planet. What's interesting, though, is the blank spot in the middle, which shows this planet here, which was initially missed by the Kepler pipeline. And my student found this, but he was scooped actually by the Planet Hunters website. So this is called Planet Hunters 3B, C, and D. And what you can see here is that this one displays transit timing variations that are much larger than the duration of the transit. And so if you were to fold this on a periodic ephemeris that smears out the signal, that fouled up the Kepler pipeline. There's plenty of signal, although this star is actually quite variable, so that caused problems too. So these transits, though, you can see are fairly blue, so they're deep enough you could spot them by eye. And that's what happened on the crowdsourced website, Planet Hunters, that's part of this universe. And the interesting thing is that these times of transit are anti-correlated with the times of transit of this planet. And you can't see variations on this scale, but I'll show those in a second. This one is low enough signal to noise and weakly interacting enough with its companions that it doesn't show evidence of variations in the times of transit. Okay, so this is kind of the first system I'm going to drill deeper in. It's located here in the Kepler field of view, which is about 10 degrees by 10 degrees in the sky. I'm also going to later talk about another system if I have time. And Planet Hunters 3 is a nice example of how to measure masses of transiting planets with transit timing variations, which are unfortunately subject to a degeneracy between mass and eccentricity. And so the strength of gravitational interactions depends on mass and separation. The eccentricity affects the shape of the planet's orbits, and so it affects how far apart they are when they go through conjunction. And so then that affects their the amplitude of the gravitational interactions. Now, what makes this a problem, actually, is the fact that when you measure the times of transit, you're only getting a snapshot of the planet's orbit every orbital period. So it's a perfect alias, which is a problem. And so the strongest transit timing variations, the ones that you see in this Planet Hunters 3 system, this is 65-day orbital period and 125, so they're close to a 2-to-1 period ratio. And so if you take the difference between twice the frequency of this planet and the frequency of this planet, you get a very low frequency or long period, and that exactly matches the period of this sinusoid. And so it's that resonant interaction. It's actually not in resonance, but it's close to enough to the 2-to-1 resonance that plays a strong role that can constrain the masses of the planets. The variations of the middle planet constrain the mass of the outer planet, and vice versa, because every planet is accelerated by everything else in the universe, and acceleration is independent of one's own mass. So the frequency of the transit timing variations scales as 2 pi times what I'll call the PTTV for period of the transit timing variations. And that for particular resonance scales as integer j times frequency of the inner planet minus j, in this case, plus 1, because they differ by 1, 2-to-1 times the frequency of the outer planet. And just to make clear, n1 is equal to 2 pi over the period of the inner planet, and n2 is equal to 2 pi over the period of the outer planet. Okay, so the problem is that because this frequency depends on the frequency of the inner planet, when you look at the transits of that planet, it's sampled at this frequency, and so you can only detect variations at the frequency of the outer planet times different integers. Likewise, the outer planet, because it transits at its frequency, this term is always going to be the same value as a function of time, and so you'll only be sensitive to harmonics of the inner planet. And just to make that clear, let me show an example of this. So gravitational interactions induce variations that scale as the difference between the frequencies of the two planets. And the term that is independent of eccentricity scales as the difference between the two frequencies times different integers. So I plotted here for the inner planet at the top, just an example of a sinusoidal variation at twice the difference in frequency between the two planets, which is known as the synodic frequency time as a function of time. And then I've also plotted the resonant term, and this actually is dependent on the eccentricity of the two planets. On the bottom, for the outer planet, I've plotted n1 minus n2 times t, so the difference in frequencies times time, and then sine of n1 minus 2n2, the resonant term, times time in red. And so the problem comes that when you sample this outer planet at the frequency and time of its transits, that's going to be an integer multiple of its period. And so the n2 and n2 terms are both constant at every single time that outer planet transits. And so those two terms give you exactly the same transit timing variations. Likewise, for the inner planet, you're only sensitive to the transits, the frequency of the outer planet. This is 2n2 and 2n2. And so that gives also exactly the same transit time variations. One of these terms is sensitive to mass. The other one is sensitive to mass and eccentricity. And so this leads to a mass eccentricity degeneracy, unfortunately. Now, the phase does change with the eccentricity, and so that gives you an extra constraint. But typically, you see the phases anti-correlate between these two between pairs of planets in the Kepler data. So I'm going to ignore this inner planet because it doesn't interact as much. But this shows now the transit time variations of that initial planet that was missed found by the Planet Hunters team, and then this outer giant planet, which shows amplitudes of around 10 minutes. This one's about 300 minutes amplitude. And so you can see they anti-correlate. The period's just set by the resonant term, and so that doesn't give you a constraint in the system. And so you basically get a measurement of two amplitudes. But you're trying to constrain 6 quantities. You're trying to constrain the mass ratio of the two planets to the star, their eccentricities, and the longitude of periastron, which measures the orientation of the orbit with respect to the observer. So it's an under-constrained problem. And so that leads to a mass eccentricity degeneracy. So 2 mass ratios, 2 eccentricity vectors at 6 parameters. The amplitudes that you measure depend on the mass ratio of the companion planet to the star, and then it depends on the period of the transit timing variations for the eccentricity-free term. There's factors of order unity in here. While it depends on some of the eccentricities times some other factors, which I haven't included here, times the period of the transit timing variations squared. The period of the transit timing variations is long. You can see it's about the duration of the Kepler data because there's roughly one sinusoid over that time scale. So even with small eccentricities, this second term can be large. And so it can affect your measurement of the mass ratio of the planets. OK, so this has been pointed out in a very nice paper by Yoram Lithwick several years ago. There's a, yeah. This is period of the inner for the inner planet and period of the outer for the outer planet. Yeah, yeah, it should be dimensionless, right? Yeah, I've dropped several factors in there just to fit it on the line. OK, so that degeneracy means that if you just have good enough data to measure the sinusoidal signal, which is typical for many Kepler planets. This is one of the best signal-to-noise transit timing variations because the amplitude is so large. So if you could just measure that long time scale resonant signal, then this degeneracy leads to the following measurements of masses, which are extremely poor. So the outer planet, this is a Markov chain Monte Carlo. This is a 68% contour limit. And the mass eccentricity degeneracy goes right through the center of this contour. So you can trade off eccentricities of the two planets with their masses. The middle planet, the one that Planet Hunters found, has a wide range of possible masses. And so you need another constraint. And so you can, if you looked carefully at this plot, you may have noticed that there is something additional going on. There's this up and down variation. And it turns out that that variation is at the frequency, the difference between the two planets' orbital frequencies. So it's not resonant. Because it's not resonant, it actually has a much shorter period. It's at the period of this outer planet, actually, or close to that. They're not exactly 2 to 1, so it's not exactly that. And so this has been referred to as chopping because it alternates earlier and later. That gives you an extra constraint. It constrains the mass of the outer planet, and it's weakly dependent on eccentricity, so you can get that mass without this mass eccentricity degeneracy. And so when you add that constraint in, you get this yellow region in which, assuming eccentricity is 0, which is actually not a bad approximation for this system, this is the uncertainty from that chopping measurement and when the mass of the outer planet is. And you can see that these don't overlap, but this contour actually is strongly affected by the prior distribution. In addition, the analytic formulas suffer from some slight error because the mass of this planet is so large that it turns out linear terms aren't quite good enough. Okay, so now if you combine these two constraints of chopping and resonance, then you get this much smaller region, 68% contour region, and you can measure the masses of both planets. Really, you're using the mass of this outer planet to break this mass eccentricity degeneracy, and you get the mass of the inner planet. And when I say inner, I actually mean that middle planet. I'm ignoring the innermost one at 34 days. So these planets are at, this is the one at 65 days and the one at 125 days. You can also do all this with n-body integration, and we've developed code that's based on a symplectic integrator. The name was inspired by CMB fast. It's called TTV fast. It's something like 20 times or faster than previous codes that we were using a Brillish Store integrator. You have to get the transit times very accurate, so you want to do high order precision integrations. But it turns out that if you combine a symplectic integrator, which basically alternates a Keplerian drift for the planets and then a gravitational kick, that does well enough, although you have to do a few things to get it to work properly. You need a symplectic corrector, which gives you a high accuracy in converting from physical coordinates to symplectic coordinates. The transit times, we could speed up the calculation by, in the symplectic integrator, you take uniform time steps. The transit's going to occur sometime in between 2 time steps generally, so you have to interpolate to find when the time of transit occurs. And if we just take, in successive steps, take a Keplerian orbit forward and Keplerian orbit backwards and average those as a function of time weighted by their distance from the 2 steps, then we get a accurate enough time of transit. And you can tune the step size to get the accuracy you need. The other thing that actually really helped speed things up is when you do symplectic integrator, you're solving Kepler's equation over and over again. But each time step, there's a very small change in orbital elements. And so you can use the previous 3 steps, fit a quadratic function for the eccentric anomaly, and extrapolate what the next time step should be. Then you only need 1 iteration of a Quartic solver to get to machine accuracy in 1 iteration. So that actually proved to be really useful in speeding things up. And this code you can find on GitHub if you're interested. And it can do any, it can basically do any dynamical problem that you're interested in which you have a hierarchy of masses and 2, small bodies orbiting a large body, and you can have any number of bodies that you want. It can do radial velocities as well, for example. Okay, so you can do an n-body model of this, and you get this blue posterior, again, 68% confidence, which you can see agrees extremely well with the analytic. The analytic, though, does have a bit of an error due to the fact that it's the mass of the outer body is large enough that you need to take into account second-order effects in mass, which we didn't do yet. Not at all. Oh, yes. So the orange contour, basically the reason it moved is that the resonant term that we're using is not is an analytic approximation which is not quite accurate enough. So it's so yeah, let me maybe 2 slides. Yeah. Oh, what? So the blue actually came first. That was in the original discovery paper of Planet Hunters. And then we were trying to understand where the mass constraint came from. And so we went through, the resonant term had already been published. And so it was just this chopping signal that we derived. And so after the fact, we were able to get agreement with this blue region. We've now tried this in other systems, and in many cases it works extremely well in the limit that the analytic formulas are accurate enough, which is generally for low mass planets. This one is kind of pushing the envelope for mass because it's more like a Saturn mass. This yellow region actually assumes 0 eccentricity for that chopping term. We've now added, oh, sorry. No, well, so actually, I did this n-body analysis for Planet Hunters, which allows eccentricities to vary, and that's where this blue posterior came from. So we did a full n-body analysis. There's still some degeneracy between the eccentricities, but the masses were fairly well constrained. Yeah. Any other questions? Okay, so so now this chopping formula that we derived and published, this assumes this is 0th order in eccentricity. We just added a paper on the archive this week, which I'm going to advertise, which does this to 1st order in eccentricity. It actually is more accurate than the Lithwick et al. Formula. TTV faster, yeah. That's not what we called in the paper, but that's what it is on GitHub. And so basically, you can derive the 1st order eccentricity formula. I did this a slightly different way than what's usually done. Usually you write down a Hamiltonian, you take the derivatives, or express it in terms of orbital elements, take the derivatives with respect to the orbital elements, and then calculate the variations in those, and then from that get the transit time variations. I actually just worked with the force equations directly and used Cartesian, polar coordinates for each planet. I did assume plane parallel. That's usually good enough for most transiting planet systems, multiplanets, because if they're all transiting, they probably lie in the same plane. You get forcing frequencies at 1st order in eccentricity that scale as an integer j, which you have to do an infinite sum over. But the coefficients drop quickly with j, so you usually only need a few terms to get an accurate formula. And then plus or minus the frequency of the one or the other of the planets. This works well for many Kepler systems, which are near but not in resonance. It breaks down in resonance, but there's very few systems that, if any, that appear to be in resonance. And it depends on the period ratio and the longitudes of periastron, and that's all incorporated in the formula. So if you're interested in this, you're welcome to use that on GitHub. Okay, so now we've taken this 1st order eccentricity formula and repeated the analysis with Planet Hunters 3. And we still get this discrepancy that the n-body, this is just what it was used to be a blue contour, is now red. This is mass of the outer planet, mass of that middle planet. The analytic formula with 1st order in eccentricity gives you a larger posterior range. And again, this is because the mass of this outer planet is a little too large to do perturbation theory. If you decrease the masses of the 2 planets by a factor of 10 and decrease the noise by a factor of 5 and rerun these simulations, the n-body and the analytic formula agree extremely well in measuring the masses of those 2 simulated planets. The bottom left show the eccentricity vectors E sine omega c, omega's missing, and E cosine omega c, E sine omega b, and E cosine omega b. Again, the black is the analytic formula, red in this case is the n-body, and there's fairly good agreement between those. Not perfect though, and that's partially because it's 1st order in eccentricity and 1st order in mass. In this case, it actually looks like the 2nd order in mass terms affect the result. Okay, and so we've now applied this to some other Kepler systems which show more than one frequency. So this is in a paper that's probably going to appear on the archive in the next couple of weeks, I hope, of Kepler 177, period of a transiting planet, almost 7 days, 49 days. n-body gives masses around 6 Earth masses and 15 Earth masses for the 2 planets. The analytic gives 5 and 13 or so. This shows the transit timing variations, which vary by of order an hour or so, versus the Kepler mission lifetime for the inner planet, and this one for the outer planet. And you see here there's a parabolic trend, which probably would turn into a sine if you could, if we could have extended the life of Kepler. But then there's also a chopping signal that's seen. These are close to a 4:3 period ratio. And then, let's see, here's another system. We've just analyzed Kepler 26. M-body gives 9.4 and 11.4. The analytic model gives 10 and 12 Earth masses. So within 1 sigma, they're consistent. This also shows the black is the model, green is the data. I should have said in the last one as well. And you can see jumps that are part of this chopping. These are close to a 3:2 period ratio. They're actually even closer to 7:5. And we've now derived a second order in eccentricity term, which is in prep. And when we add that in, we get a better agreement than if we just use a first order eccentricity analytic approximation. So we're doing the analytics after the M-body, but it's building confidence in the M-body. And we're planning to apply this more widely to the Kepler transiting planets that show transit timing variations with companions that also show anti-correlated transit timing variations. So this is really a work in progress. The goal, of course, is to get a mass-radius relation for a range of planets. And what is being found is that, like in the Kepler 36, there's a diversity of systems. Some planets look rocky, and some appear to have gaseous envelopes. OK, so now I'm going to completely switch gears and talk about a different system, KOI 3278, which is this part of the Kepler field. And this all relates back to our quasi-periodic transiting search. So we found, even though we're looking for dynamically interacting planets, that we're coming up with other things. One example is that there are eclipsing binaries that during the periastron passage, you can get tidal effects that cause a short-term variation. These are known as heartbeat stars. We found lots of these in our search for planets, as have other groups. And the usual case when you run the Katz periodogram, you fold it, realign the transits, is you get something that looks like this. So this shows already a known KOI from the Kepler catalog, KOI 3278, very high signal to noise in total, period of 88 days. And this shows the realigned transit centers in hours. So this transit lasts about 5 hours. So our initial strategy was to search as I mentioned, the systems with known planets. My student has been, Ethan Kruse has been working on this. In particular, we're trying to improve our rejection of correlated noise within the data. So the data have a lot of features that are really hard to flag and get rid of. And so he's been doing a great job on that. Right now, what we've settled on is we do a fit to a transit shape with varying depths and durations multiplied by a polynomial. And then we do a fit just with the polynomial and take the difference in likelihoods between those two. And then we feed that into the quasi-periodic transit search algorithm to then line up the pulses within the range of slop that's allowed. OK, so when Ethan he masked this planet and then reran the pipeline, he found this really weird-looking planet candidate. It has this pulse and then a dip. And what the code was doing, it's looking for transit. So it was fitting this with a transit signal. The difference between the blue and the red lines is the difference between the model and some polynomial. And I believe he's averaged some data with time, which is why it shows some noise still. This didn't look right, though. He sent me this late at night. And so I said, well, why don't you switch the sign of your code? And he did so, and out popped this. It was a transit that brightened rather than dimmed, which harkens back to my second slide on when you get a transit versus when you get microlensing. This turned out to be the first example of a self-lensing binary. This pulse has exactly the same period as this dip, and this is not a planet. This is a white dwarf, as it's eclipsed by a G star. And then half an orbit later, when the white dwarf goes in front of the G star, you get magnification because the Einstein ring is much larger, in this case, a couple by a factor 2 or so, than the radius of the white dwarf. And not only do you get a microlensing event, but you get 16 microlensing events in the duration of the Kepler data. There were 16 pulses and 16 eclipses that were detected. This is actually something I had worked on as a Chandra fellow, as I mentioned. And again, these are one and the same phenomena. It's just that usually you can neglect the lensing effect. Other white dwarfs have been found in which the passage of the white dwarf in front of the companion star shows a dip because they're much shorter orbital periods, so their semi-major axes are smaller, so their Einstein radii are smaller, and so occultation dominates over lensing. So this is the first example where lensing dominates over occultation, and you get a brightening rather than a dimming. Mm-hmm, certainly. Because I had written papers on this, and so I was hoping to find lensing events at some point. I had actually done searches and hadn't found any. Ethan was still looking for transits, and so what happened was the egress of the white dwarf off the star, causing this dip, was translated by his code into the ingress of a planetary transit. Because we're fitting a polynomial, that kind of took up the slot, but obviously, gave a very poor fit. But it was flagged because it actually gave a better fit than just a polynomial. Does that answer your question? Or yeah. Okay. Yes, and but the reason I said switch the sign was that it looked like this may not be a real transit feature. It was actually this that was causing the delta chi squared. And so by changing the sign, then instead of fitting to dips, he fitted to peaks, and then that picked it out right away. Yeah. At much higher signal to noise, it was a better fit. So this is actually just the folded data once we realized what it was. Both of these are about a part in 1,000, which is actually just a coincidence because this depends on the temperature of the white dwarf and this depends on its mass. And you can use these data to, well, this is just a cartoon of what the geometry of the system. So you have a G star and a white dwarf that are orbiting one another. When the white dwarf passes in front, you get gravitational magnification leading to this pulse. There's still some flux contributed by the white dwarf throughout, and so when the white dwarf goes behind the G star, it disappears, and you get that occultation, which was initially flagged as a transiting exoplanet. Okay, so you can use these data to measure the mass of the white dwarf. This is kind of a cartoon of how this works. The magnification of these pulses, if I neglect limb darkening, then it would just look like a top hat profile. And it turns out there's an approximate lensing theorem that you can show that when the lens is off the source, you get almost zero magnification. And as soon as it goes on the source, you get a magnification that scales as twice the Einstein radius squared divided by the radius of the source squared, in the limit that the Einstein radius is much smaller than the size of the source, which applies in this case. The magnification is only a part in 1,000. Usual gravitational microlensing is much higher magnification. That's how you detect it as it varies with time. This isn't showing the dip here, but if you just take the pulse components and add up their area, in this case I showed 2 orbital periods, and then the duration of the pulse scales as twice the radius of the star divided by the relative velocity. And here I've neglected limb darkening, and I've assumed a central eclipse where it's going across the equator of the star. Okay, so then you can calculate the area of this red region, and one of the powers of the radius of this G star in this case drops out. And so you get, let's see, 4 times Einstein radius squared divided by the velocity. But the Einstein radius squared scales in proportion to the semi-major axis. And so if I integrate the green curve, which is the flux, the unocculted flux over one orbital period, then the orbital period is 2 pi a over v. So that scales in proportion to the semi-major axis over v. And so when I take the ratio of the red to the green areas, semi-major axis and velocity drop out, and I just get left with the mass of the lensing object, the white dwarf, divided by the radius of the source star. And then there's a factor of order unity if it's not a zero impact parameter. You have to correct for that. So this gives you a way to measure the mass of the white dwarf. There's also a factor that's caused by the occultation of the white dwarf, but that's small in this case. So I can just plug this in. The main star turned out to be a G star, so it's roughly a solar mass. The signal was a bit smaller than this, is about 3 times 10 to the minus 6 is the ratio of the fluence in the red to the green. And so the mass of the white dwarf is about 0.6 solar masses, like many white dwarfs. You can then fully analyze this system. We don't know the temperature of the secondary eclipse. So we don't have a way to measure the size of the white dwarf. So I had to make a few assumptions to figure out the parameters of the system, and these will be dropped as we get more data. So as we measure radial velocities or measure the color of the secondary eclipse, you can break some degeneracies, and so far we've done that with models. So I assumed a Padova isochrone, and this is density versus effective temperature of the G star. I've assumed a mass-radius relation for the white dwarf. So with that mass from the lensing, I then estimate its radius. And then from the depth of secondary eclipse, that gives me the temperature of the white dwarf. From that, I get an age, a cooling age of the white dwarf, again, model dependent, unfortunately, but which then tells me how long the white dwarf has been cooling since it finished its red giant phase. The third assumption that I had to make, unfortunately, was that an initial final mass relation for the white dwarf. So given its 0.6 solar mass, I assumed I think you get about 2 solar mass progenitor. And then from the main sequence in red giant age of that progenitor, I get the total age of the system. So with the total age of the system, then, and with the effective temperature of the G dwarf from its SED, I can pin down its density. With its density, then it turns out I can measure the impact parameter of the white dwarf. So that gives me these 1 and 2 sigma confidence limits on the properties of the G dwarf. Yeah, Tim. No. Oh, okay. Yes, it does. And models indicate that it should be very negligible, but that was something I worried about a lot. But at 88 days, it's a fairly long period. I mean, it probably did go through a common envelope phase, but it probably didn't last that long. Otherwise, it would have spiraled into a much shorter orbital period. But yeah, that was something I worried about, and it would be nice to get more data to be able to check that assumption. I'm sorry?
Should have been more compact initially.
And then spiraled out?
Well, because due to the mass loss.
Oh, yeah. But the common envelope phase might have spiraled in, so it's unclear what the initial orbital period was. And I did use the BSE models, and I believe I had to start it with a much longer orbital period initially to end up at 88-day orbital period. Okay, so and so this is actually how I could estimate the fact that this is a G star. Let me see if I can. So with the parameters of the system, the star turns out to be fairly similar to the sun. So I took a snapshot image of the sun and then simulated what this might look like if you could see it in high resolution. I actually turned the orientation of the sun so it would go across sunspots, because that makes the lensing a little more interesting. But you can see the Einstein ring visually here. It's about twice the radius of the white dwarf. And so the magnification is twice the Einstein radius squared, so it's about a factor of 8 greater than the occultation caused by the white dwarf. The outer part of the sun actually gets lensed within the Einstein ring, so there's an inversion here. And so the white dwarf is blocking some flux from the star that's filled in within the Einstein ring. And so you have to account for that in the analysis, which you did. And here you can see as it passes over the edge, you can kind of see the shape of the, I'll just play it one more time. And the impact parameter turned out to be about 0.7 of the stellar radius. So, all right, takes a while to get all the way across the sun. Let's see what else I wanted to say about this. So the typical case, the Einstein ring is much smaller than than the lens or the foreground planet, and so you don't even notice the magnification. You might notice it kind of near the edge, but in most planet cases, that's so small it's negligible even in the very precise Kepler data. Okay, so let's see. This system was a bit of a surprise to find, because if you plot binaries which contain a white dwarf and a main sequence star, it's kind of an outlier in 2 parameters. This is the mass of the companion star. You can see a lot of these companion stars are M dwarfs. There's a reason, because M dwarfs are red, so they're easy to find. White dwarfs, when they're young, are hot and blue, and so you get 2 different, two different colors. And so with the Sloan Digital Sky Survey and other surveys, it's easy to pick these out. There is one case of a K dwarf companion to a white dwarf. But the other thing is that in orbital period, this is a log scale. This is a very large outlier. At 88 days, all these other post-common envelope binaries are within a few days orbital period. So we found very, very few systems like this, and it was lucky to find one that actually went through eclipses and lensing. We've been searching the Kepler data to see if we can find more of these, and so far have not been able to find any. And others have searched. Jason Rowe, who's part of the Kepler team, has done a search, and he's come up empty with other self-lensing binaries. They may still be there, but it may just be that stellar variability swamps the signal. Well, they should still be there. Okay, so to summarize, the quasi-periodic automated transit search algorithm, or COTS, or CATS for short, has been successful so far in finding some planets initially missed by the Kepler pipeline. Many of these actually were, with more data, later found by the Kepler pipeline. And so I think we're getting to the point of diminishing returns, but we still have some systems like that Mars-sized one that I showed you that we're working on analyzing. In the case of the Planet Hunters 3, missing that was initially was too bad, because the huge transit time variations are the first case where we can, or one of the first cases where the chopping provides a measurement of the mass. There are other cases with larger planets in which we can measure chopping, because you get a bigger signal, and so you get better signal to noise. But this is a fairly small planet. About it's also consistent, like Kepler 36c, with being low mass, meaning Neptune, about 5 Earth masses, but it's much bigger than a rocky planet. We've been developing tools for further TTV analysis, and now we're working on applying those to other systems, and I gave you a couple examples of that. And in the process of looking for transient planets, we've stumbled upon the first repeating microlensing event, and that hopefully will help constrain models of common envelope evolution.